Okay, now we're ready to go ahead and start solving some equations. This first example, notice that I have an exponential expression on the left-hand side. Um, More or less all the exponential equations we solve in this class are going to be one of two types, this being the first one, the more prevalent type. What you want to do is start by isolating your exponential term. We only have one term, it's on the left-hand side, it's already isolated. So now what I need to do is figure out how do I get access to that exponent. We're going to go ahead and use our inverse property. So I'm going to take the natural log of both sides of my equation. I can do this because exponential and logarithmic functions are one-to-one. So taking the natural log of both sides, what do I get on the left-hand side? Natural log and e, again, they're inverses, they cancel each other out, and I'm left with 4t is equal to the natural log of 20. Okay, now I have to solve this equation for t. This is an easy one. T is a linear equation to the first power. Solve it by dividing both sides by 4. So t is going to be equal to the natural log of 20 divided by 4. The directions ask us to write our answer rounded off to 3 decimal places, so I need to compute this. So I'm going to take the natural log of 20 and make sure you close parentheses. If you don't close parentheses and you do the natural log of 20 divided by 4, you're going to get the natural log of 5. So natural log of 20 divided by 4. And I come up with 0.7489. Going out 4 decimal places, rounding back to 3, I get 0.749. So t is equal to 0.749. This example here looks a little bit more complicated, but it is essentially solved the same way. I have one term with an exponent in it. I'm going to isolate this term right here. Okay, so in order to isolate it, I need to get rid of the 5 and the 6. I'm going to move the 6 over first, so I will add 6 to both sides. And we have 5e to the 0.3x plus 1 is equal to 36. And now to get rid of the 5, I'll divide. So we have e to the 0.3x plus 1 is equal to 36 divided by 5, or 7.2. Okay, now we're in the same position, or the same place we were at the previous example. I will take the natural log of both sides of my equation. This is going to get rid of my exponential function here, or it's going to give me access, bring my exponent down. And so the left-hand side now simplifies to 0.3x plus 1 is equal to the natural log of 7.2. I think it's a good idea right now to go ahead and compute the natural log of 7.2. So I'm going to come over here and natural log 7.2, close parentheses, enter. And I have 1.974 and a bunch of other stuff. Okay, so how do I finish this problem off? I'm solving it for x. Notice that this is a linear equation. So what do we have to do to get x alone? I'm going to have to subtract 1. And then I also have to divide by the 0.3. You know, this is not an algebra class. I don't need to see all those steps. So come back over to your calculator. You will subtract 1 equals. Notice it takes your previous answer. And then I'm going to hit divide by 0.3, enter. And I end up with 3.2469. So rounding that off, I will have x is equal to 3.247. Okay. How about this one? E to the x is equal to 0. Well, if we try using the same exact technique we just did, taking the natural log of each side, what do we get on the right-hand side? What is the natural log of 0? That's right. That's out of our domain. We can't do it. So this particular equation has no solution. I mention it because you're going to see it. It's going to crop up. You're going to try to solve it. Don't solve it. There is no solution. In addition, I want you to note that e to the x is always going to be greater than 0. It's never, ever, ever going to be a negative number or negative quantity. I mean, obviously if I put more coefficients out here or divide it by something, that could change, but e raised to any power will never be 0, and e to any power will never be a negative number. Okay, last example. This one here looks really complicated. I've got x's and exponents and e's all over the place. Turns out to be the easiest example so far. If you notice, each term has a common factor of e to the 2x minus 1. I'm going to factor that quantity out. When I take out the e to the 2x minus 1, what are we left with? I get this polynomial 3x squared plus 14x minus 5. Okay, so now I have this product set equal to 0. Keep factoring. So looking at our polynomial here, I'm going to use trial and error to factor it. So we get 3x and x, and with the 5, it's going to have to be 1 and 5 or 5 and 1. So you play around with that a little bit. 1 and 5 will work. You have to decide about your signs. Plus 5 and a negative 1 will give us what we need. You'll want to go off on the side and FOIL and double check. Okay, once we reach this point here, solving by factoring says, okay, the only way this is going to equal 0 is if one of these factors equals 0. So set each one of these equal to 0 and solve it. So e to the 2x plus 1 equals 0, 3x minus 1 equals 0, and x plus 5 is equal to 0. Let me start with this one here because it's the easiest. Subtracting 5 from each side, we end up with x is equal to a negative 5. So there's one solution. Over here, 3x minus 1 equals 0. You should be able to do these steps in your head. You're going to add 1 to each side, divide by 3. So x is equal to a 1/3. Now we got another solution. How about over here? E to the 2x plus 1 is equal to 0. That's right. It can never, ever, ever equal 0. It does not give us any additional solutions. So I have two solutions. X is equal to 1/3 and x is equal to a negative 5. Okay, now we're going to look at solving logarithmic equations. Again, there are many different types that you would come across in a college algebra class. And here, I'm more or less only concerned with one type of logarithmic equation. So that's the type we're going to focus on here. Okay. Remember that the natural log is log base e. So I have log base e of x is equal to 4. The log rule, or definition of a logarithm, says the base raised to the exponent must equal this number here. So using that definition to rewrite this without logarithms, I end up with e to the 4 is equal to x. Do whatever it is you have to do to solve this equation now for x. This one's pretty simple. I've already got it solved for x, so it's just a matter of, should I leave my answer as e to the 4, or do I have to write it as a decimal? The directions specified around your answer to 3 decimal places, so I'm going to plug it into my calculator and figure out what e to the 4th is. So again, in order to use my e key, down here, second function, ln, gives me my e, 4, and I have 54.5981. Rounding this off to 3 decimal places, we have x is equal to 54.598. Okay. All right. How about this example? Well, it's pretty much the same, except for what I'm taking the log of is a little bit more complicated. But that's it. Everything else is going to stay the same. So I still have my log is equal to a number. I'm going to use my log rule. So e raised to the 0.15 is going to be equal to 2x minus 9. Now e to the 0.15 is a real number, so let me compute that quantity. I have e raised to the 0.15 gives me 1.1618. So 1.1618. Don't round it off. I'm going to write down a few digits, knowing that there's more. That's equal to 2x minus 9. Alright, so what do I have to do to solve this for x? It's a linear equation. I'm just going to have to add 9 to both sides and then divide by 2. Once again, this should be done on your calculator. So show me a few intermediate steps, but I don't want to see everything. Notice that my previous answer, e to the 0.15, is still on my calculator, so I will hit plus 9 equals, and then divide by 2. I have 5.0809. Rounding back to 3 decimal places, I will use x equals 5.081 for my answer. Okay, almost done. 2 more to go. On this example, I have natural log, got one term. So I said, well, if it is isolated, if I have the natural log is equal to some number, I know how to deal with it. So that's what we're going to do. Manipulate it first to get it into that form. So the 16 and the 10 have to go. A very common error, students will take the 16 minus 10 to get a 4. We can't add these together. We can't subtract them. They're not like terms. The 10 is multiplied by this expression. So I'm going to have to bring the 16 over by subtracting 16 from each side. And then I can get rid of the 10 by dividing by 10, or in this case, negative 10. So dividing through by the negative 10, I now have the natural log of x minus 1 is equal to, reduce that, plug it into your calculator, decimal fraction, I don't care. In this case, obviously, you want to go the decimal, 1.6. Now we're ready to do the log rule. So we have e to the 1.6 is equal to x minus 1. I'm going to evaluate e to the 1.6 in my calculator. So I have e raised to the 1.6 equals 4.953, and I need to add 1 to that expression. So I get 5.9530. Rounding off to 3 decimal places, x is equal to 3.953. All right, here we go. Last one. Natural log of x is equal to 0. This is not going to be no solution like we had for the exponential function. This one has a solution, has a real number solution. Let's work it out. Same technique we've used. I've got the natural log is equal to a number. So let's convert it using the log rule. I have e to the 0 power is equal to x. What's e to the 0 power? X is equal to 1. Okay, so that's the last one of solving our equations. Again, a few things I want to make note of as far as solving equations go. We're simplifying it to just the type that we're going to be using this class, this semester. A few other things to know about logarithms. When you are taking derivatives, often we're going to want to use our properties of logarithms to expand them, put them in another form, which will make it much easier to apply our derivative rules. Also, as far as domain is concerned, for the exponential function, domain is going to be all real numbers, but with logarithms, our domain is going to be only non-negative numbers, 0 to infinity. All right, I hope it didn't kill you. Look forward to seeing y'all in class.